Welcome to the chapter Real Numbers. This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to explore Euclid's division lemma, identify rational and irrational numbers, state fundamental theorem of arithmetic, explain decimal expansions, prove irrational numbers, state laws of logarithms. Introduction. Before you enter into the lesson, follow the instructions shown on the screen. Click each tab to know more. We learned from previous classes that natural numbers are the set of numbers which start from 1. They are denoted by n. Example: n is equal to 1, 2, 3, so on. Whole numbers are the set of numbers that include 0 along with the natural numbers. They are denoted by W. Example: 0, 1, 2, 3, and so on. An integer is a whole number that can be positive or negative or 0, but it should not be a fractional number. It is denoted by letter Z. For example, Z is equal to -3, -2, -1, 0, 1, 2, 3, and so on. Now, let us recall about rational and irrational numbers. Rational numbers are the numbers that can be expressed in the form of p by q, where p and q are integers, and q not equal to 0. They are denoted by q. Always, rational numbers are expressed by using terminating decimals or non-terminating repeating decimals. Example of rational numbers are as shown on the screen. Finally, we conclude that rational numbers contain the set of natural numbers, whole numbers, and integers. We also have irrational numbers which cannot be expressed in the form of p by q, where p, q are integers and q not equal. You know that rational numbers contain the set of natural numbers, whole numbers, and integers. But do you know that rational numbers are contained in some other set of numbers? Let us learn about various properties of rational and irrational numbers in details, and also about logarithms. Let us know about Euclid's division algorithm. The algorithm name itself suggests us to do with divisibility of integers. It simply states that if any positive integer x is divided by another positive integer y, then it gives remainder z which is smaller than y. Let us do an example. Suppose if x is equal to 22, y is equal to 5, then the remainder z equal to 2, which is smaller than y. The result obtained by division process is quite easy to understand, but it has got many applications relating to divisibility properties of integers. Let us learn few of them which are mainly used to calculate HCF of two positive integers. Now, let us learn about Euclid's division lemma by considering a puzzle. A trader was moving along a road by selling cups. An idler who did not have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket with cups and dashed it on the floor. The cups broke. The trader requested the panchayat to ask the idler to understand the Euclid's division lemma more clearly. Let us do the problem by considering following pairs of integers. A. 28. B. 17, 5. Consider a bit that is 20 and 8. Here A is equal to 20, B is equal to 8. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 20 is divided by 8, we obtain quotient Q as 2 and remainder R is equal to 4. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Similarly, let's consider second set of numbers 17 and 5. Here, A is equal to 17, B is equal to 5. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 17 is divided by 5, we obtain quotient Q as 3 and remainder R is equal to 2. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Sir, in Euclid's division lemma, the term lemma sounds differently. I never heard about it. Lemma is the typical word to hear and pronounce, but it is just a result. It is used in proving the other theorems. Suppose one wants to compute the HCF of two numbers. The most common method used is factorization. But to compute the factorization of large numbers, such as 65,842, 24,895 and so on, is very difficult and takes a lot of time. So Euclid has came up with a theorem that would help us to find the factorization method easily in less time. This theorem is very simple and is just another form of divisibility rule, which we have studied in our lower classes. Sir, could you please explain us the theorem of Euclid's? Okay, listen to the theorem statement. Now, let us know theorem on Euclid's division lemma. State the Euclid's division theorem is algorithm. An algorithm is a step-by-step procedure or formula for solving a problem. The word algorithm has come from the name of the Persian mathematician Al-Khwarizmi, earlier transliterated as algorithm or algorithm. The word algebra is also derived from a book which he has written called Hisab al-Jabr wal-Muqabala. Euclid's division algorithm is used to compute the highest common factor flowchart. Here, let us know sequentially in the flowchart to keep the steps to find the HCF. Let the first number be A and second number be B. If A is greater than B, then according to Euclid's division, lemma A is equal to BQ plus R, where Q and R integers and 0 less than or equal to or less than B. Suppose A is equal to BQ plus R. If R is equal to 0, then B is the HCF of positive numbers A and B. If A is equal to BQ plus R, if R not equal to 0, we apply the division lemma to B and R and continue the. Now, let us do some examples by taking small numbers first and then large numbers. To understand the Euclid's division lemma more clearly, Let us find the HCF by considering following pairs of integers. A. 24. Step 1. 20 is equal to 4 into 5 plus 0. As the remainder is 0, the process stops. The divisor at this stage is 4. Therefore, HCF is equal to 4. So, 4032 is equal to 262.8 into 1 plus 44. As R is equal to 44, which is not equal to 0. Apply Euclid's division lemma to 58 and 44. Step 4. Here 58 is equal to 44 into 1 plus 14. As R equal to 14, it is not equal to 0. Apply Euclid's division lemma to 2 into 7 plus 0. Euclid's division lemma or algorithm has several applications in order to find the properties of numbers. Let us do some examples. Show that every positive integer and b equal to 6. By substituting the value of b in EDL, a equal to bq plus r, we get. By substituting r equal to 3 in equation 1, we obtain a equal to 6q plus 3. By substituting r equal to 4 in equation 1, we obtain a equal to 6q plus 4. By substituting r equal to 5 in equation 1, we obtain a equal to 6q plus 5. Solving the above equation. Problem 3 is that use Euclid's division lemma to show equation 1.1.1. Case 2. If r equal to 1, then a is equal to 3q plus 1. By cubing equation 1.2 on both sides, we get a cube is equal to 3q plus 1 whole cube. As it is in the form of a plus b whole cube, we write it as shown. Now, by further solving, we get a cube is equal to 9m plus 1. Let us represent it as equation 1.2.1, where m is equal to 3q cube plus 3q square plus q. Case 3. If r equal to 2, then a is equal to 3q plus 2. By cubing equation 1.3 on both sides, we get a cube equal to 3q plus 2 whole cube. 4. Show that exercise problem. Let us solve exercise problem. Exercise problem. Let us see a discussion between Raju and Rajesh about real numbers. Raju: Rajesh, are all integers also included in real numbers? Why? Rajesh: Yes, Raju, I will. Be proved that the infinity of the real number is a bigger infinity. Raju: Thanks, Rajesh, for. In order to know in detail about real numbers, Exploring real numbers. Let us first know about prime numbers and composite numbers. Prime number. A prime number is any number greater than 1 and has exactly two factors, 1 and itself. Examples: 2, 3 are primes because they have exactly two factors, 1 and itself, and are on the screen. But here 4 is not a prime because it has more than two factors, 1, 2 and 4. Examples are as shown on the screen. Composite numbers. Composite numbers are the numbers which have more than two factors, that is the number 1, the number itself, and at least one other number. Examples are as shown on the screen. Note: 1 is neither prime nor composite. We know that all natural numbers except 1 can be written as a product of their prime factors. For example, let us go through some of the numbers. Say 3 is equal to 1 into 3. 6 can be written as 2 into 3. 253 can be written as 11 into 23, and so on. But here 1 is neither a composite nor as shown. Let us try with another number. 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written in the following form as shown. Here the numbers 3803 and 3607 are primes. By this we can prove that a composite number can be written as the product of primes. Here are some examples as shown on screen. If the numbers taken has all the positive Exploring real numbers. Statement of fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of powers of primes, and this factorization is unique, apart from the order in which the prime factors occur. Let x be the composite number. Let us factorize it as shown, where x is equal to p1, p2, pn are the primes. If we use same primes, we get all the powers of primes. When the primes are arranged in ascending order, we get it as p1 less than or equal to p2, less than or equal to p3, so on up to pn. Then the factorization number is unique. For example, 163800 is written as shown on screen. Exploring real numbers. Now, let us consider an example. Here, let us consider a composite number 2310. Writing the number 2310 in terms of product of primes, we obtain as follows. So the product of primes of 2310 is 2, 3, 5, 7 and 11. Prime factorization method. This method involves finding the prime factors of a given number. This method is used to find the highest common factor HCF and the least common multiple LCM of the given number. Let us look at an example. Now, let us do some example problems on prime factorization method. Find HCF and LCM of integers 12, 18 by the prime factorization method. Solution. Consider the positive integer 12. To find its HCF, express it as a product of 2 and 6. Here 2 is a prime number and 6 is a composite number. Now, the composite number 6 can further be expressed as the product of two prime numbers 2 and 3. In this way, the number 12 is expressed as a product of find the least common multiple of 12, 18. To find the least common multiple of the given numbers, consider the number 12 among the given numbers. It can be written as the product of least common multiple 2. The number 18 can be written as multiples of 2. The number 6 is further expressed as a factor of 2, keeping the other number unchanged. At this stage, the two numbers can be expressed as factors of the least multiple 3. Now, the obtained numbers are prime in nature. They cannot be further factorized in terms of numbers other than 1 and themselves. The product of all these prime numbers is shown on screen as the least common multiple of the given numbers is equal to product of the greatest power of each prime factors in the numbers. States that consider the numbers 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. The number 4 power n does not end with 0 because it should be divisible by 5 or should contain a prime number 5 in prime factorization. But it is impossible with this as 4 power n is equal to 2 to the power of 2n, so 2 is only prime in the factorization of 4 power n. As there is no number 5 as prime factor and there is no natural number n for which 4 power n ends with the digit 0. Show that 12 power n cannot end with the digit 0 or 5 for any natural number n. The number 12 power n does not end with 0 because it must be divisible by 5 or 10 and should contain a prime number 5 in prime factorization. Exercise problem. Knowledge check. Attempt the following questions to check your understanding. Let us discuss about rational numbers and their decimal expansions. Decimal expansion is classified into terminating and non-terminating. The non-terminating is further classified into repeating and non-repeating. Let us discuss each in detail. The word terminate means end. A decimal that ends is terminating decimal. In other words, a terminating decimal has a finite number of digits after the decimal point. To know the theorems on prime factorization method, click each theorem tab. Let x be a rational number whose decimal expansion is terminating. Then x can be expressed in the form of p by q, where p, q are co-prime and the prime factorization of q is of the form 2 power n, 5 power m, where n, m are non-negative integers. By 1000, that is equal to 375 by 10 cube. Similarly, the terminating decimals 1.04 and 12.5 are expressed as follows. Write the following terminating decimals as rational numbers. Solution. 55 and 0.4 is expressed as shown. We conclude that any rational number that has a decimal expansion which terminates is expressed as a rational number whose denominator is a power of 10, where 2 and 5 are the only prime factors of 10. Therefore, during simplification of rational number, we observe that the number is in the form of p by q. Let x is equal to p by q be a rational number, such that the prime factorization of q is of the form 2 power n 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Now, let us solve some examples based on the theorem. Is that rational number of the form p by q, where q is of the form 2 power n 5 power m, to an equivalent rational number of the form a by b, where b is a power of 10, where the prime factorization is in the form of 2 to the power n 5 power m, and n, m are non-negative integers. Let us solve some example problems on non-terminating recurring decimals in rational numbers. The word non-terminate means never end. A decimal that never ends is a non-terminating decimal. Now, let us learn a theorem on non-terminating repeating decimal. For example, let us consider decimal conversion of 1 by 7, which is non-terminating and recurring decimal. But as the quotient is repeating itself, it is denoted by a bar. Since denominator is 7, which is not of the type 2 power n 5 power m. Let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 power n 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, recurring. Example 3. Using the above theorems, without actual division, state whether the following rational numbers are terminating or non-terminating repeating decimals. Solution. By the theorem, let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 power n 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring. 1. Here 16 by 125 is expressed as 15 by 5 into 5 into 5, which is in turn expressed as 16 by 5 cube, which is the terminating decimal. 2. Similarly, the decimal expansion of remaining numbers is as shown on screen. Example 4. Write the decimal expansion of the following rational numbers without actual division. The decimal expansion of the following rational numbers is as follows. Now, attempt the following problems. You can click Answer tab to verify your answers. Exercise problem. Let us solve exercise problem. You can click Solution tab to verify your answer. Now, let us know about irrational numbers. A number is said to be irrational if and only if the number can't be written in the form of p by q, where p and q are integers and q naught equals to 0. These are the numbers which express a fraction into a decimal by the division method. Here, even if the division process continues indefinitely, a zero remainder is never obtained. These decimals never repeat and never terminate. Let us look into some examples that we are familiar with. Let us prove real numbers to be irrational with the help of fundamental theorem of arithmetic. We will also prove that root 2, root 3, root 5 and in general root p is irrational, p is a prime. Before proving, let us state and prove with the help of fundamental theorem of arithmetic. Consider the following theorem. Its statement is, let p be a prime number if p divides a square, then p divides a, where a is a positive integer. The proof of this statement is based on the fundamental theorem of arithmetic. Let a be a positive integer. Hence a is equal to p. P is one of p1, p2 till pn. Now, since a is equal to p1, p2 till pn, therefore p divides a. Let us use this theorem to solve a sample problem. Let us solve some more example problems on irrational numbers. Verify the statement proved above for p is equal to 2 and p is equal to 5 and for a square is equal to 1, 4, 9, 25, 36, 49, 64 and 81. From 36, 49, 64 and 81. Therefore, the statement is incorrect. Example 3. Show that 5 minus root 3 is irrational. Let us assume, to the contrary, that 5 minus root 3 is rational. But this contradicts the fact that root 3 is irrational. This contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational. So, we conclude that 5 minus root 3 is irrational. Example. Show that 3 root 2 is irrational. Assume the given one is rational. So by the above statement, co-primes a and b not equals to 0 can be found such that 3 root 2 is equals to a by b. Rearranging, we get root 2 is equal to a by 3b. As a and b are integers, we get a by 3b is rational, and so root 2 is rational. But this contradicts the fact that root 2 is rational. This contradiction has arisen because of our incorrect assumption that 3 root 2 is rational. Example 5. Prove that root 2 plus root 3 is irrational. Solution. Let us assume root 2 plus root 3 is rational. Let root 2 plus root 3 is equal to a by b, where a and b are integers and b not equal to 0. Therefore, root 2 is equal to a by b minus root 3. Squaring on both sides, we get as shown. Let us solve some exercise problems. Knowledge check. Attempt the following questions to check your understanding. properties of real numbers. We have gone through many of the examples to show whether the number is rational or irrational. Suppose A, B, and C represent real numbers. Find whether real numbers satisfy the listed properties or not. Or, do they hold for the operations of subtraction and division? Take as many real numbers you want and investigate. Usage of logarithms is in calculations of engineering, science, calculating compound interest. Logarithms are used for all sorts of calculations in engineering, exponential growth and decay, pH value in chemistry, measurement of the magnitude of earthquakes, etc. Introduction to logarithms. Before going to learn about logarithms, we need to recollect laws. Understand logarithms, a good knowledge of laws of exponents is required. In the given example, the power or exponent or index and base are shown on screen. Now, let us learn about the need of logarithms. We know that any composite number can be expressed as product of powers of prime numbers. Suppose we want to multiply 27 with 81. One way is to multiply both the numbers directly. The other way is to use the rules of exponent. The product of 27 and 81 can be written as 3 power 7 according to the laws of exponents as shown on screen. Similarly, if we want to divide 81 with 27, we obtain the number 3 as per the laws of exponents. Therefore, for replacing multiplication with addition and for replacing division with subtraction of numbers in exponential form, logarithms are necessary. Now, let us know what a logarithm is. Writing exponents as logarithms. For example, 10,000 can be. So, writing a number in the form of a base raised general case, if a power n is equal to x, then logarithmic form of it is log x to the base a equal to n, where a and x are positive numbers and a not equal to 1. Similarly, the exponential form of log x to the base a equal to n is a power n is equal to x. Example, the logarithmic form of 2 cube is equal to 8 is shown on the screen. Now, let us solve a sample problem on logarithms. Write the logarithm form of 64 is equal. Let us solve a sample problem on logarithms. Determine the value of y in log 2 to the base 8 is equal to y. Solution. The exponential form of above logarithmic function is as shown on the screen. Knowledge check. Attempt the following question to check your understanding. Write 10,000 in exponential form and identify the base and index. Here, as 1000 can be written as 10 to the power 4, where base is 10 and index is 4. Find product of 25 and 125 without actual multiplication using exponents. The solution is as 25 can be written as 5 square and 125 can be written as 5 cube. Then the product of their equivalent terms will be equal to 5 power n, which is in turn equal to 3125. Express 128 and 32 as powers of 2 and find 128 divided by 32. Solution. By factorizing 128, we get 2 power 7 and for 32 we get 2 power 5. Now, by dividing equivalent terms of 128 and 32, we get as shown. Attempt the following question to check your understanding. Show that a power 0 is 1. So log 1 to the base a is equal to 0. Since a power m by a power n is equal to a power m minus n, put n equal to m in equation 1. Then as shown, so the logarithmic form of a power 0 equal to 1 is log 1 to the base equal to 0. Logarithmic form of 11 square equal to 121 is. Here the answer is log 121 to the base 11 equal to 2. Laws of logarithms. There are three types of laws of logarithms. First law tells us how to add two logarithms together. Consider two exponents x is numbers. This is first law of logarithms. Note that the logarithm of 1 to any base is always 0. Example, log 1 equal to 0. And the logarithm of a number to the same base is always 1. Example, log 10 to the base 10 is equal to 1 and log e to the base e is equal to 1. Now, let us solve a sample problem on this law. Example, second law. Obtained by multiplying the logarithm of the number by that power. Let us solve an example problem based on the second law. Example, simplify log 5 cube to the base 10. Third law. Example, log x by y to the base a is equal to log x to the base a minus log y to the base a. This is third law. It states that if we want to divide two numbers and find the logarithm of the result, we can do this by subtracting the logarithms of the two numbers. Let us solve an example problem based on third law of logarithm. Example, expand log 18 by 65. Write log 10 plus 2 log 3 minus log 2 as a single logarithm. Now, finally represent the above equation in terms of second law. Therefore, the single logarithm of the given expression is log 45. Write 2 log 3 plus 3 log 5 minus 5 log 2 as a single logarithm. The solution for the above problem is as follows. Knowledge check. Attempt the following question to check your understanding. Since the given expression is in the form of log xy equal to log x plus log y, we can write it as shown on screen. Given 4 power 3 equal to 2 power 2 whole power 3. By solving, we get 64 equal to 2 power 6. Therefore, its logarithmic form is log 64 to the base equal to 6. Exercise problem. Let us solve exercise problem. You can click Solution tab to verify your answer. Knowledge check. Attempt the following questions to check your understanding. Applications of real numbers. Real numbers helps us to count and measure quantities of different items. You dial real numbers in your mobile phone to call a friend. Real numbers can be thought of as points of physical sciences. Most physical constants such as the universal gravitational constant and physical variables such as position, mass, speed and electric charge are modeled using real numbers. Try to solve the problems in the practice zone on your own. N 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let x is equal to p by q be a rational number, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring. The square root of any whole number is either a whole number or an irrational number. Let us list out the formulas used in this chapter. The three laws of logarithms are: log xy to the base a is equal to log x to the base a plus log y to the base a. Log xy to the base a is equal to log x power m to the base a is equal to m log x to the base a. Follow-up work. Rational numbers are terminating decimals or a non-terminating, repeating decimals. Prove that 3 plus 2 root 5 is irrational. Expand log root x cube by y square. Determine the value of log. Test your understanding of the chapter by taking the mock unit test. You have successfully completed the chapter Real Numbers.